Our last speaker is Daniel Ray, who studies biophysics at the University of California in San Diego. His advisor is Henry Barbanal, and his practicum was at Lawrence Livermore National Laboratory.
All right, thanks. So my work is concerned with the problem of bridging the gap between our computational models and the real world. Specifically, it focuses on the process known as data assimilation in the geophysical sciences, in which we blend these models together with experimental data in order to generate predictive forecasts. So there are many challenges faced when performing this task, and I'm in particular interested in addressing the issue regarding the adequacy of the observation system that's used to collect the data. This problem is known as observability, and simply stated, it might be summarized with the question of how many observations are needed to achieve accurate forecasts. Many systems exhibit critical thresholds in the resolution of the observations below which the forecasts degrade considerably. And as part of my research, I've developed a computational framework for identifying these limits and analyzing how they scale with certain parameters of the problem. The results provide evidence for the role of chaos in determining where these critical limits lie and have a number of useful implications in both theory and practice. In particular, I will briefly touch on 3 applications of interest to the Department of Energy, namely coupled Earth systems models, power generation networks, and biophysical applications involving mapping the neural pathways in the brain. So I'll ask you to consider the situation of a typical modeling application where you spent a great deal of time and effort developing your models and are now faced with the challenge of applying them to experimental data. For instance, as a way of either validating the correctness of the model or for generating the forecast needed, among other things, to help bring together and make better and more informed policy decisions. Regardless of the application, predicting the system's behavior requires knowing how to initialize the states and parameters of your model. These variables cannot often be directly measured and therefore must instead be inferred from your experimental data. This inference process involves solving a Bayesian inverse problem that fuses the model and the data together into an optimal estimate of the system's state. The diagram on this slide illustrates the general process. It requires 2 inputs. The first is a computational model that describes the evolution of some representation of the state of the system. These models are typically physical, but they can really be anything. They can be statistical, phenomenological, or data-driven, say based on some sort of deep learning architecture. The second, you also need a model for the observation process itself that relates the data that you have to the state of the system in your model. And you also need a data set of dynamical data that's obtained from a network of sensors. The data assimilation process proceeds in 2 steps: an analysis in which the new data is incorporated into the estimate, and a forecast in which the resulting estimate is then fed back into the model as an initial condition to generate a prediction. And the whole process can then be cycled by updating the forecast with additional data to improve the estimate. And this is, for instance, how a weather forecast is produced, in which you collect new data each day and use that to update the current forecasts. So these forecasts have a number of uses in addition to their predictive value. They can also be used to validate the model by comparing against additional measured data. And they also provide useful feedback to help improve the experimental design. So this issue of observability has been well studied, particularly in the area of optimal control. And this has led to the development of some rigorous conditions for determining when it is possible, in principle, to determine the state of a system given the available data. However, those conditions tend to be somewhat inadequate for large, complex problems, as there are many that are technically observable, which turn out to be too ill-conditioned in practice. And in some sense, the data assimilation process is always at odds with this problem of ill-conditioning. As inverse problems, they're typically ill-posed in that they're underdetermined. In other words, there's not enough information in the observations alone to extract the signal from the noise. This problem can be remedied, or is remedied, by introducing additional information in the form of regularizing constraints. And these constraints come from prior knowledge and can often be rather arbitrary, particularly when no other information about the system is available. In our case, however, we have another tool at our disposal, namely the forecast model that describes the time evolution of the system state. And this model represents all of our scientific knowledge about the problem and provides access to an indispensable source of prior information that's stored in the waveform of the observations. By using the model trajectories to constrain the space of possible solutions, we are often able to determine the hypothetical true state of the system from noisy data without any additional a priori information. And while this is promising, it's also worth noting that improperly imposing these constraints can also make a trivial problem for which we already know the solution, essentially computationally intractable. And this is especially common when the system is chaotic, so small deviations in initial conditions grow exponentially along its trajectory. And this sensitivity injects dynamical instability into the estimation process, which needs to be controlled using information from the observations. Otherwise, there's little hope that the forecast will be accurate. And suppressing these instabilities becomes increasingly difficult when the measurements are sparse. In particular, there appears to be well-defined critical thresholds in the resolution of the observations, below which the estimation process is effectively guaranteed to fail. Although these thresholds are inherently complex, they're largely determined by the chaotic properties of the system. And so one of the goals of my research has been to develop computational tools to identify these thresholds and analyze how they scale with certain aspects of the problem, such as the resolution of the model and the choice of the estimation algorithm. And this information is useful in a number of ways. Theoretically, it helps us sort of better understand what are the fundamental limits on our ability to solve a large class of ill-posed dynamical inverse problems. While in practice, they're used to help validate the overall system design and identify areas that need improvement. So I'll now demonstrate these ideas in the context of a dynamical system that was introduced by Ed Lorenz in 1996 as part of his study of the problem of predictability as a function of the spacing of weather stations around the globe. This model may be viewed as a crude simulation of the atmosphere on a periodic lattice. It contains advection-like terms as well as dissipation, forcing, and it is chaotic for certain parameter choices. The model has found wide use in the meteorological community for two reasons. First is that its dimension can be chosen freely, simulating the freedom that one has in choosing the resolution of models involving spatially extended systems that are typically found in discretizations of partial differential equations. Second, the chaos in it is extensive in the sense that the fractal dimension of the attractor grows linearly with the resolution of the model. Critical thresholds in computational observability are identified by running a series of experiments on the observation system. These experiments use simulated data, which allows us to make the rather expedient assumption that the system dynamics are known perfectly, so there's no systematic error in the forecast model, only stochastic errors added directly to the data to simulate noise in the measurement process. So although these assumptions are clearly unrealistic, the setup is still useful for testing the viability of the observation system, because if we can't achieve adequate results under these idealized conditions, there's little chance that we'll be able to do it when we have real data. So we identify observability thresholds using a sampling procedure in which the estimation process is viewed as a series of Bernoulli trials with two outcomes, success and failure. A trial is considered successful when its root mean squared error synchronizes below the noise level. The symmetry of the problem allows us to reduce the resolution of observations in a systematic manner using binary search to identify the critical limit in observability where the estimation fails. This process is then repeated, sampling over random initial conditions while incrementally increasing the resolution of the forecast model. So we first perform this procedure using a data assimilation algorithm known in the meteorological community as 3D VAR. This method operates by recursively optimizing the estimate using newly required data each day, and it is one of the simplest and most widely used techniques. It provides a good baseline for comparison. The plot shows the critical limits, which I call L sub c, as a function of the dimension of the model. And right away, we see there's a well-defined threshold that scales linear with the number of degrees of freedom in the model. And furthermore, the slope of this line agrees quite closely with a time average measure of the chaotic instabilities in the forecast model. So what does this mean in practice? Well, typically the number of observations is fixed, at least in the short term, by the instrumentation. So if we draw a line on the plot to denote the number of available observations, these results provide guidance on how high we can set the resolution of the forecast model before the forecast will start to consistently fail. Alternatively, if you have a target model resolution in mind, these results give guidance on how best to choose the existing observation system to achieve these goals. It also turns out that for this threshold of 40 to 50% of observation coverage is specific to 3D VAR methods, which suggests the question of whether this requirement can in fact be reduced. And the answer is that it can, for instance, using a related method known as 4D VAR. We see that it significantly decreases the density of required observations. So 4D VAR methods have been in use at operational meteorological forecasting centers in Europe since the early 2000s, and they're one of the main factors driving the recent success of European models. The main benefits stem from the fact that they analyze measurements taken over several days instead of just using the new observations taken since the last forecast. This allows the algorithm to exploit information stored in the waveform of the time series data in a way that enhances the effective resolution of the observation network without the cost of, say, launching additional satellites. Now, as you might expect, there are limits to these benefits, which inevitably come at the cost of additional computational complexity, and decisions about whether these extra effort is worth it will ultimately depend on and have to be made on a case-by-case basis. The point of all this, however, is that there is a need to start thinking about our model and our data together in terms of their ability to achieve our scientific goals. And the framework outlined here provides a simple way of analyzing these interactions in a way that helps assess the viability of our existing observation, analysis, and forecasting systems. So, of course, in the real world, things aren't so straightforward. The models are typically orders of magnitude more complex and subject to unknown errors as well as exogenous shocks. And as such, our goal has been to sort of build in the complexity into this analysis framework sort of piece by piece. With that, I would like to briefly touch on 3 application areas of interest to the DOE. The first being coupled Earth systems models, which relates to the DOE's ongoing accelerated climate modeling for energy project. These models attempt to characterize the coupled interaction between the 5 Earth systems that have the most impact on forward climate projections. And on our end, we've decided to start with ocean systems, which are some of the most simplest and well understood, and applying this analysis to a core set of differential equations underpinning global climate models, namely the shallow water equations, indicate that success in that case requires observing roughly 2/3 of the dynamic states. However, this threshold can be reduced by over half using a 4D VAR method, and this is important when you consider that while the height of the ocean surface is easily observable using satellite altimetry, the local tangential velocities of the surface currents must be deduced using Doppler shift techniques and are therefore inherently more noisy. Furthermore, we also showed that the use of GPS trajectory recordings from drifting Argo floats, essentially buoys that float along the surface and send satellite signals back, can also further reduce this requirement on satellite coverage. The second area of application involves one of the DOE's central missions, namely ensuring the safety and reliability of U.S. power systems. In particular, the continued adoption of renewable resources brings with it a need for better identification and control over the network demands. The reliability of the power grid requires synchronization of its components, but systems driven by renewable resources like solar or wind naturally introduce shorter-term fluctuations into the grid, which makes them inherently less reliable than existing systems built on fossil fuel-driven turbines. So an important issue going forward is the development of a control system to suppress these short-term instabilities. And success in this endeavor depends on our ability to observe, model, and forecast the system's behavior. And I'll be working on some of these issues during my postdoc in collaboration with some folks from Argonne. And finally, a number of biophysical applications are also starting to emerge. Among these, the DOE has joined the BRAIN initiative in 2017, investing several $million towards the two objectives. One is developing specialized measurement tools for high-resolution neural recordings, and two is building an integrated computational framework for analyzing the dynamic and multimodal data. Mapping the brain's functional connectivity, however, requires fusing together structural information with dynamic electrophysiological data that spans multiple scales. And success in this endeavor will require new analysis techniques which combine the data assimilation's model-based approach with data-driven counterpart in machine learning. And these two paradigms can sort of be seen as complementary limits of the same Bayesian inverse problem. So despite the obvious differences between these applications, the observability of these systems is a common issue that requires the development of computational tools like the ones proposed here to help inform and direct the development of new experiments, measurement devices, and analysis techniques. And these studies, which target the collaborative development of our models, observation systems, and algorithms, will be of increasing importance going forward, especially as we start to transition to the new era of data-driven modeling and exascale computing. So with that, I would like to thank especially the CSGF for, I wouldn't have been able to do half of this stuff without the freedom that the fellowship has given me, as well as my advisor and all of the fellows. Thank you.